Hi, and welcome back to Allen High School. We're in the midst of our discussion of electrochemistry at the AP/IB/HL level. Now we're setting up cells and looking at two half reactions and deciding which one wants to be oxidized and which one wants to be reduced. In our last video, we did the spontaneous example. I want to do at least one example of a non-spontaneous reaction. So we've got our two half reactions, and the E0 values for these, the reduction potentials, is 0.34 volts for the copper plus, and it's a minus 0.40 volts for our cadmium situation. Now, here's how I like to do it. I first figure out what wants to be reduced and what wants to be oxidized. Remember, the most positive one wants to be reduced, the most negative one wants to be oxidized. Now, that's what would happen if it was spontaneous, but the question specifically said non-spontaneous. So instead of oxidizing, I'm going to let cadmium be the reduction. Instead of reduction, I'm going to let this be the oxidation. So I think that's a better approach than trying to memorize signs. I figure out what spontaneous would be, then I do the opposite. It's kind of like figuring out what your parents want and then you do the opposite. And so that tends to be what teenagers sometimes do. Okay, let's take a look at this. So our reduction half reaction is now cadmium 2 plus 2 electrons going to cadmium. And I'm going to keep the E0 exactly as is because these were reduction potentials. And I'm going to reverse the copper so that copper solid is being oxidized to copper 2 plus 2 electrons. And, this is a pretty easy one to balance. Same number of electrons. We don't need any coefficients. Now, since I reversed the reaction, I have to change that sign. And when I add these up, I get negative 0.74 volts, which is perfect because the question said non-spontaneous, and a negative indicates non-spontaneous. My balanced reaction would be copper plus cadmium 2 plus yields copper ion plus cadmium. My delta G is equal to minus N F E0, which is minus 2 because there were 2 electrons involved. After you balance it, you go after you balance, 96,500, and then a minus 0.74 volts. And once I calculate this, you get 1.43 times 10 to the 5th joules, which is 143 kilojoules. All right, so that's how you would do, and positive. And you notice again, that sign is further evidence that we did it correctly because a positive delta G is non-spontaneous. Now, I think you have the idea, so I'm going to forego our next example, but I'm going to go ahead and give you the values I came up with so that you can check yourself and you'll know whether you need to ask me questions in class. So this is what I got when I calculated it, and hopefully that's what you get too. All right, now let's move on to non-standard concentrations. All right, we're going to focus on non-standard concentrations as opposed to non-standard temperatures. And to do that, we use the Nernst equation. And I want to teach you how to use the Nernst equation both qualitatively and quantitatively. Now, this applies to all temperatures. And we've got E0, we've got our non-standard. I think you know what all these symbols are by now. You should know what Q is. If we are at 25 degrees Celsius, all of these little constants in here, so if I take these constants and change natural log to log base 10, this is the formula that we get, and it's the most commonly used formula. Right now, why would we go natural log to log? Well, back in the day, log base 10 tables were a lot easier to work with on our little slide rulers or in the tables. You just push a button, so y'all don't really care anymore. But That's the way we used to do this. All right, let's first take a look at this situation here. We want to calculate E of the cell. When the cell that was described previously, and so this was in a prior number or problem, so I'm going to set it down right now. It was zinc 2 plus. It says it was described previously, but I have a feeling I deleted that. And this was at 1 molar, so let's first start with that one. Salt bridge, copper 2 plus, okay, 1 molar, and copper. So this was an original cell that we were looking at, that we could look at. Very, very common to use. You'll look at it, I think, in your lab. Now, what we want to do is to predict what would happen if we changed our zinc ion to 1 times 10 to the minus 4th. So let's first talk about Le Chatelier. I think it is a reasonable way to discuss this. Let's write our reaction. So we have zinc going to zinc 2 plus, and we have copper ion, right? They read just left to right, going to copper. So that's our balanced equation. Let's get our little line that's kind of our trick for Le Chatelier. So there's our line. That represents our equilibrium or our 1-to-1 molar situation there. Now, what happens if we decrease our zinc ion? If we decrease our zinc ion, that's the stress on the equilibrium. So the stress is on, some of you said it was a stress on the product. The stress is on the whole reaction. Okay, so that's our stress. The question is, what do we need to restore the equilibrium? Well, if you decrease product, you have to form new product to compensate or to replenish that. So we're going to have to form new product. Well, the only way to form product is to consume reactant. Okay, now this is a voltage producing reaction. It's plus 1.10 volts. So we are shifting to the voltage producing side, and therefore we expect E naught of our, or E of our cell, not E naught, E of our cell to be greater than E naught. We expect it to be greater than 1.10 volts. So by decreasing the concentration of zinc ion in the zinc cell, we could potentially get more voltage out of the system. Okay, so that is one way to do this. Now let's take a look at predicting from a formula. I want to clean this up a little bit. And I think maybe it would be better to do this in a new video, and we'll do these two together. So until then, this is signing off.